Let's do some multiplication and division. We already know how to do some multiplication and division. We know how you can like split up or combine radicals under a multiplication, and in fact we use that every time we rationalize the denominator, right? Like in the last example, we needed to do that. Up here when we said that root 3 times root 2a was root 6a, we're saying, all right, I'm multiplying, got the same index, right? Square root. I'm multiplying them, so I just put the product under a single square root. So that's our basic rule that we're going to follow here. So some of these we kind of already know how to do. Root 5 times root 2. Yeah, root 10. And by the way, if you were doing a problem like this and you just went straight to root 10, I'd be like, great, right? Like it's not poorly communicated because you didn't write out the product inside. The cube root of 6 times the cube root of 4. Well, we got the cube root of 6 times 4. Now, I am choosing specifically to write that as a product because my next step is actually to factor further. You know, root 10 we can't simplify because there's no pairs of the same factor. But I want to make sure that I'm looking to see maybe I can simplify this radical further. So 6 is 2 times 3 and 4 is 2 times 2. So as it turns out, I've got 3 2's, so that means they turn into a single factor of 2 outside times the cube root of 3. So what we see here is when we're multiplying, you know, the cube root of 6 and the cube root of 4 independently are already reduced, right? Like there was no groups of 3 of the same factor that we could use to simplify each of these, but of course when we multiply them, sometimes we see that a group of 3 emerge. Let's do another one. These are fifth roots, and you'll notice each of the individual roots are simplified. There's no groups of the same, 5 of the same factor in either of these individually. So let's see what we get. 8 is 2 times 2 times, you know what? Let me do this. 2 cubed. And then we have a cubed b to the 4th times 8 again, so another 2 cubed times a squared times b cubed. I'm going to just simplify the expression inside. I've got 2 cubed times 2 cubed, so that's 2 to the 6th. What's my power on a? Yeah. And how about the power on b? Yeah. And now this will be much easier to simplify. When I talk about, when we say like we need 2 of the same factor to bring one out, or in a fifth root 5, a group of 5 of the same factor to bring one out, what we're really saying is I need a perfect 5th power in order to bring one out. So right off, we can look at that and say, well, I've got an a to the 5th inside a 5th root, so this I can just grab. And then I've got a 2 to the 6th and a b to the 7th, so I certainly have 5th powers and a little bit left over. I'm going to do this out in 2 steps, but you might find that you do this in 1 step from here, and that's fine. This 2 to the 6th I'm going to write as 2 to the 5th times 2, and I have a to the 5th. And then b to the 7th I'm writing as b to the 5th times b squared. So I've got a 2 to the 5th, an a to the 5th, a b to the 5th. What goes outside the radical? 2ab. What's left inside? 2b squared. Yeah. Oh, that should be a 5, not a b right there. Are we having fun? Good. Good. Let's do some more. All right, so this one a little bit more interesting because we have some subtraction happening and a factor there. How do we begin a problem like this?
Inside the parentheses first.
Sure. I like that idea, and if we did it, we'd have nothing to go on. I mean, like, I like that idea. Like, we look to see if we can simplify. But as it turns out, like 3 root 5 and 4 root 2, like, they're already simplified radicals, so we can't actually do that subtraction. Like, the expression inside the parentheses is already simplified. But I like your thinking there.
Distribute.
We can distribute. Yeah, so let's distribute this. And when we do so, we now just have a couple of products that look kind of like the ones we were doing on the previous page. You know, we just get to evaluate these products individually. So this first product, what does that become? 3 root 10. What's that? Yeah, so minus 8 because, of course, root 2 times root 2 is 2, and we're multiplying it by the factor of 4 that's already there. And that's as simplified as it gets, right? The radicals that are in the only radical, right, that is involved in this expression is already simplified. So not much we're going to do there. Oh, root 2 times root 2 is equal to 2. Like, we use that fact when we simplify radicals. Like when we rationalize the denominator, for example, here we said, oh, I'll multiply by root 2a on the top and the bottom, specifically because when you multiply a square root by itself, it just gives you the thing inside. So when we have, root 2, so I could have rearranged this to say 4 times root 2 times root 2, right? The order in which we multiply things doesn't matter. So then I can say, well, that's equal to 2, and then I multiply it by the 4 that's already there.
Root by itself, it just becomes the number inside.
A square root by itself, yeah. Other questions? Okay. How do we do this one?
Multiply this.
Yeah, well, so yeah, multiply, it'll require us to FOIL. So something squared means I multiply it by itself. We all know, and we are becoming very good at resisting any temptation we might have to distribute an exponent over addition, because we know we're not allowed to do that. So we're going to just multiply 3 plus root 5 times 3 plus root 5. You can use FOIL, or I'm a fan of the little table here, so I'm going to set this up. So 3 times 3 is 9. 3 times root 5 is 3 root 5. 3 times root 5 is another 3 root 5. Root 5 times root 5? 5. Now, something interesting happens. We're used to when we would use this technique to like FOIL out expressions with x's and stuff. You know, we were used to like having like terms on this diagonal, but now we have like terms on both diagonals, right? We have our constants on the opposite diagonal. So we got 9 plus 5. Well, that's 14, and then we have 3 root 5 plus 3 root 5. What does that give us? 6 root 5. So that's the product, is 14 plus 6 root 5. Right, let's do one more product. This one's interesting because we are multiplying two radicals that have different indices, right? We have a cube root times a square root. So when this happens, when I'm working on a product that looks like this, I actually start by using the exponential form. So, you know, the cube root is a 1/3 power, and the square root is the 1/2 power. I want to be able to write it as a single radical. So when we think about what that means in terms of an exponential expression, in its exponential form, if I want to write it as a single radical, then that means I want to write this as something raised to a single power. I want to get basically a common denominator of those exponents. And in fact, so I've got the 1/3 power and the 1/2 power. I'm going to rewrite the 1/3 power as the 2/6 power, right? The common denominator here is 6, times 5 to the 3/6 power. Now I've got, I could rewrite this as 2 squared times 5 cubed. I'm ignoring the denominators for a moment, and then say I'm raising this whole product to the 1/6 power. If you do a quick check, you should see that these are equal. Like, I think we've done a bunch of problems where we've started with an expression like this and gone this way. Right? We would distribute this across the product, and that would bring us back there. So this is the 1/6 power of this product. That means it's the 6th root of that product. Are you all right? Yeah? Oh, 2 squared, 5 cubed. You're not getting sick, are you? And 2 squared times 5 cubed, 4 times 125 is 625? I feel like that's wrong. No. 4 times 125, oh, 500, okay. Maybe I'm getting sick too. And this was a nice numerical example, which means we could check, you know, if you're suspicious of this and you're like, you know what, I don't know, man. We can find the cube root of 2 times the square root of 5. And then we can find the 6th root of 500. The same. Okay. Let's do a couple of division problems. We're going to start with a super simple one that we've done before when we were just simplifying radicals. We said we need to rationalize the denominator. And so if we saw a radical in the bottom, like 1/√3, our basic strategy, and we've already used it at least a couple times today, is let's multiply the top and bottom of this fraction by √3. You know, √3 is the problem there, so I just multiply by √3, top and bottom. I do that because on the bottom I have a square root multiplied by itself, and we know that just gives us a number inside, so we get √3/3. That's old news. Now we're going to apply this same idea to a fraction that looks like this. I don't just have a single radical in there, but I'm adding or subtracting an expression that involves, you know, some terms that involves at least one radical. So, you know, look at this, you might think, well, if I multiply by √3 and √2, maybe that will take care of it. As it turns out, it won't. You could try it. You'll see you'll still be left with radicals in the denominator. What will work, though, is if you multiply by the conjugate of this expression in the bottom, and the conjugate is what you get when you just change whatever that operation is in between, change it. So it's subtraction right now. Its conjugate would be √3 plus √2. So we're going to multiply the top and the bottom by √3 plus √2. What's that? Not a perfect square, a difference of squares. It's like how a difference of squares would factor, and that's exactly why we do this. So I'm going to set up my little table. So there's my √3 minus √2, √3 plus √2, Root 3 times root 3 is 3. Yeah, and then we have root 3 times negative root 2. Yeah, negative root 6. Root 3 times root 2. Uh-huh. Root 2 times negative root 2. Negative 2. So just like, that's okay, just like we saw before when we were doing our FOILing, I have like terms on both diagonals. What happens on this diagonal with the radicals, though, these guys cancel. That's equal to 0. And that will always be the case. Those terms with the radicals will cancel. That's why we choose the conjugate to multiply by. And then going the other way, we have 3 minus 2, so that's just equal to 1. So going back here, this is now our denominator here is 1. And the top is just root 3 plus root 2. And of course, may as well just go ahead and write this as root 3 plus root 2. Again, this is a numerical example. You could check on your calculator. 1 over root 3 minus root 2 will be equal to root 3 plus root 2. Just got to make sure you put parentheses around that denominator in the calculator. One more. Let's use the same technique. Let's rationalize this denominator. What should we, how should we start? Say that again?
Using the conjugate.
So what is the conjugate of the bottom?
Root 6 minus root 2.
And we multiply by that on the top and the bottom. So I got a couple of products to find here. I'll do the bottom first. So I got root 6, root 2, and then root 6 minus root 2. Root 6 times root 6 is 6. Root 6 times root 2 is root 12. Root 6 times negative root 2 is a negative root 12. And negative root 2 times root 2 is negative 2. So again, these radicals terms cancel. And we've got 6 minus 2, which is 4. So that's what goes on the bottom. On top, let's see. 3 root 6 minus root 2, and then root 6 minus root 2. Root 6 times 3 root 6, what should that give us? $18. Yeah, 3 times 6. Root 6 times a negative root 2 is a negative root 12 again. 3 root 6 times a negative root 2 is just a minus 3 root 12. And negative root 2 times a negative root 2? 2. Again, we have our like terms arranged on both diagonals here. The radicals don't cancel each other here this time, but we don't care about that. That's fine. We're totally fine with having radicals up top. We just wanted to get rid of them on the bottom. So we have 18 plus 2, which is 20, and then minus 4 root 12. And, we're not quite done this one because, like anytime we're giving a result that ends up being a fraction, we should check to make sure that it's reduced. And like anytime we've got a result that has a radical, we should check to make sure that it's simplified. So root 12, well, 12 is 2 times 2 times 3, which means it's 2 root 3. So this guy here is 2 root 3, which means we can write this as 20 minus 8 root 3. Is that okay?
You can simplify more.
Yep. Yeah, let's, I'm gonna, I guess, just factor out a 4 from the top. So we have 5 minus 2 root 3 times 4 up top. Of course, we're dividing this whole thing by 4, and those guys cancel. And we get a nice result.